My pleasure to introduce Peter Bartlett from University of California, Berkeley, and today we'll talk about some representation, optimization, and generalization properties of deep neural networks.
Thanks very much to the organizers for inviting me. I'm delighted to be here. So I want to talk today about a family of statistical methods that have been applied with huge success to some very large-scale problems in recent years and have led to big performance improvements in problems from areas like computer vision, speech, natural language processing, game playing, things of this sort. And so these are deep neural networks, and I'd like to view them in this talk as a non-parametric method. So think about them as compositions of nonlinear functions, right? So we're computing a function from, let's say, a vector input to a vector output, and we compute it as just a composition of a bunch, m here, of vector value functions of the vector input. So we're just stacking these things one on top of the other. And there are many ways that we could think of the HIs as being computed. They could come from different sorts of families. For instance, they might be, you take a vector input x, compute a linear function by multiplying it by this parameter matrix wi, and then compute some nonlinear function of that, in this case a coordinate-wise squashing function that has this sort of shape. That's the old-fashioned style of neural networks from the last time they were popular. If you're modern, you might use a different kind of nonlinearity that looks like this, right? Again, for component-wise, you might use max pooling nonlinearities, or there are a whole variety of things. Really, all I'm using, so I actually want to view these things in a non-parametric way. So we're going to consider, at least later in the talk, pairs of layers in the computation that they perform. So it's just some non-parametric, some rich family of functions that map from vectors to vectors, and not so important the particular way that they might be computed or parameterized. But here, the typical thing is to think of these parameters that enter linearly, and then there's some nonlinearity. And crucial aspect, we're taking compositions of these things, and it's a deep composition. So M is, think of M as some big number. Okay, so why is this a good idea? Well, the jury's still out. So, the claims that are made are that this depth is useful for learning representations. So as you move from the input towards the output, you've got an effective way of representing useful features. That you can compute more complex features of the input in this sort of a way, features that are useful, perhaps useful more broadly. And it's a rich non-parametric family. We've known for a long time that we can get better rates of approximation in classical settings by nonlinear kinds of parameterizations, and there's some evidence that this depth is actually giving us a really parsimonious way of representing complex functions. There are, for instance, specific examples of functions that, if you want to compute them in a shallow network with a fixed kind of parametric approach, some of these families I've described, if you want to compute a function of that sort in a shallow network, it might take hugely more complexity in the sense of number of parameters than if you were to compute the same function, approximate the same function in a deeper network. So there's some evidence of that sort that actually this depth is really helping in terms of the approximation theoretic side of things. How compact our representation might be for useful complex functions. So these are some of the features that have been claimed for these sorts of non-parametric methods. But we should ask ourselves, well, what about optimization? I mean, you would think that having these nonlinear parameterizations should be an issue, and even more of an issue as we consider deeper and deeper networks. And we might expect that to get worse as the depth increases. And as well, if we're thinking about having very parsimonious representations because we're taking compositions of functions, well, that should make us wonder about the statistical complexity of the sorts of functions that we have, right? So, we're certainly claiming that we can approximate a rich family of functions in a very parsimonious way. So, what's the right notion of statistical complexity? And you know, how do we control that so that when we go and fit one of these networks to our training set of size, you know, 100 million, that we're actually going to do well in terms of the population. Okay, so I actually going to start by saying a little bit, just very briefly, about some results on statistical complexity, some deviation bounds here, and really that's to motivate this non-parametric viewpoint, right? To argue that we should be thinking of these things as compositions of functions from non-parametric families. And then the second part of the talk, second and third part of the talk, I want to look at some of the optimization properties of these networks, and a particular flavor of deep networks called residual networks that have, you know, become the method of choice particularly for computer vision problems. And we'll see that they have some nice properties of the optimization landscape that we're faced with for these networks has some very nice properties, and we'll look at some natural optimization approaches for a restricted family of these networks. So we're actually, you know, moving to a very simple special case for which we can prove something. Okay, so that's the outline for the rest of the talk. Let me start by saying a little bit about statistical complexity, and you know, starting off in the very classical setting where we're thinking of it in a parametric way. Let's think of a classification problem. So we're wanting to take our, let's say in a computer vision problem, our image and classify it into, for simplicity, let's say one of two classes. So, you know, all of this can easily generalize to real values or vector valued outputs, but just to simplify things, let's think about a binary valued response variable, and we're assuming that we have IID data, so XY pairs according to some probability distribution, and we want to choose some function, you know, from the class computed by a network of this kind that has misclassification probability that's small. We might want that to be near minimal over the family of functions that we're considering. And then, you know, there's I guess, a refinement of a result, 50-year-old result of Vapnik-Chervenienkis, that for some class of plus minus one valued functions defined on X, uniformly across probability distributions, we have a training sample of size n, then we can get a deviation, a result that says that the misclassification probability is bounded by the sample average of misclassification, so proportion of mistakes on the training sample, plus a penalty term that looks like the VC dimension of this class F, so a combinatorial dimension, notion of complexity of that class divided by the sample size n. It's to the power of half. You know, and I guess you can get a similar result. As a consequence of this result, you can argue that the misclassification probability is close to the minimum over the class F for the probability distribution P, you know, with a similar sort of deviation. And if you want bounds like this that are uniform, that apply for all probability distributions, for this sort of deviation inequality, if you want it to be uniform across functions in F, then you know all you can really play with is the constant C. So there's nothing to be improved. And for neural networks, the VC dimension, you know, in very broad terms, increases with the number of parameters and depends on the particular nonlinearities that you consider, and depends on the depth for different nonlinearities. And to give you a one-slide summary of that, so when we're thinking about networks with L layers and P parameters, if the nonlinearity, so again we're thinking of this specific family, the example on that first slide, right, where we have linear functions followed by a component-wise nonlinearity. If that component-wise nonlinearity is piecewise constant, then the VC dimension grows. And I've said, you know, I'm ignoring log factors here, right? So the tilde is saying that, but actually this should be a theta, that the VC dimension grows as P log P in that case. In the case of piecewise linear functions, like the ReLUs, the rectified linear units that are popular lately, the VC dimension grows like number of parameters times the depth, and that's tight. So there's an extra penalty for going deeper. And the other two cases, we actually don't know the lower bound in this case. So these are upper bounds. We don't know that they're tight. So in the case of piecewise polynomial networks, we have an upper bound that grows quadratically with the depth, and sigmoid networks, even worse as a function of number of parameters. The message here is that, I guess thinking of this case, we really have something that grows at least, the lower bound there of course applies for the other one. So we really have something that grows at least the number of parameters times the depth. So we're getting an extra penalty for the depth. And these sort of results, and in particular the implication for the misclassification probability for a network of this sort, really don't have much to say about what happens in practice, right? Where the number of parameters is typically several orders of magnitude larger than the sample size, and the depth is huge for the sort of networks that people actually use. So this sort of setting of thinking of the parametric setting and these sort of results in terms of combinatorial dimensions doesn't have much to say about the way these networks are used in practice. So the first result I wanted to mention is looking at a kind of non-parametric view of the statistical complexity of networks of this sort. This is joint work with Phil and Foster, PhD student at Cornell, and Matus Nilgarski, who's faculty at Bartlett, and they were visitors a year ago. So visitors to Berkeley. Okay, so I need a little bit of notation to state the results. I'm really only going to state it, and we're working in terms of operator norms for the parameter matrices that appear in each layer of the network. So in layer I, we have a matrix of parameters, and we consider its operator norm. So how much can a unit vector be blown up in some norm, and think of it as just the Euclidean norm, and that's the spectral norm of the matrix. And the other notation that we need is for this multi-class margin function. So think of this problem of mapping from vectors in our input space to output vectors that are supposed to represent one of m classes, right? So we have an m-dimensional output, and we consider that as being predicting a classification to class I if the ith output is the largest, right? And somehow we're using the scale of the outputs of f. We're going to consider that in the theorem that follows. So we're actually going to use some sort of a Lipschitz surrogate loss here that tells us, if we should have predicted output y, then by how much does that corresponding output exceed the largest of the other outputs, right? That's this quantity m. Okay, and if that's positive, then we're making the correct prediction, and we're concerned with the scale of this sort of quantity. Okay, so with that notation, we can state the theorem that for every f sub a, so a represents all the parameters in our deep network, so it's got L layers and L of these parameter matrices A1 through AL, and we're computing this composition of linear function A1 times the input composed with this Lipschitz nonlinearity sigma 1. I guess it doesn't have to be component-wise, so we just need that it's Lipschitz, and so on all the way through these L layers. So that's the class of functions we're considering. We can get a bound on, this is just looking at whether this correct component is largest, right? So this is misclassification probability is bounded in terms of some sample-based error, and you can think of this margin quantity being smaller than gamma, some parameter gamma, as being something like an upper bound on a Lipschitz loss, right, for our real valued class. So a surrogate loss that happens to be Lipschitz. It's one way to view this. So it's kind of turning the classification problem into a regression problem with a nicely behaved loss. So this is our criterion that we're we're thinking of on the data, and we can get a bound on the misclassification probability in terms of that statistic. And there's a deviation term that depends on L here is the number of layers, gamma is sort of the scale at which we're measuring things, N is the sample size, and R is some notion of the scale of the function that we're considering. So if we're restricting to functions FA that have this RA no more than little r, then R appears in the deviation term. So this is the dominant piece here is the product of the operator norms of the AIs. So we're just looking at how much can an input vector be blown up in moving from layer to layer. We're assuming, I guess, all of the sigma i's are Lipschitz. And there's another fudge factor there that I'm going to sweep under the rug and not talk about. And this is sort of a piece that's important that depends on sort of a little more than just this for instance, spectral norm of the matrices AI. So the thing to keep your eye on is the product of the operator norms. So we get some notion of statistical complexity that depends on this really rather non-parametric style thing, right? We're just looking at to what extent these functions scale. It really has nothing to do with the number of parameters in the class. There have been similar results from long ago for sigmoid networks. So where you think about a different kind of operator norm with these squashing functions, you have for free that the L infinity norm at the output of each layer is bounded, and the matching norm is the one norm, the max of the one norms for the rows of the matrix, and there were results of that sort as a product of those things for sigmoid networks. There's been work building on this. Noah Golovich, Sasha Rachman, and Alhad Shamir used quite a different proof techniques. They're based on Rademacher averages to give similar bounds, but with an improved dependence on the depth. If you have special cases, so a homogeneity property of the nonlinearity, that means that fudge factor term can actually be something like a constant in some cases, in these cases, rather than growing with the depth, which is nice. But I think the thing to keep in mind is that we can get a bound on risk on the complexity term, at least in the right hand side of this bound on risk, depends on this product of operator norms of the layers of the network. Okay, so for the rest of the talk, we're going to be viewing these networks in a more abstract way, I guess for this part of the talk, and thinking about them as compositions of functions, but they're just functions. We're not thinking about how they might be parameterized. And we're actually going to consider a specific family of deep networks, residual networks that give state-of-the-art performance in computer vision problems in particular that have been applied across a range of areas. So what are residual networks? How many people have come across these residual networks? Small proportion. So let me say a little bit about these, and I've stolen some slides from Kai-Ming He's ICML tutorial from a couple of years ago. So this is showing the reading from right to left, the performance on a particular image classification benchmark of the competition winners in different years, right? So as time goes by, things improve. The big improvement in performance. So these bars are showing this classification, this top 5 error rate. So smaller is better. Big decrease in moving from sift and hold, so shallow sort of methods to deep networks, and another big decrease in moving from deep networks to kind of ridiculously deep residual networks. So the ResNet was the 2015 introduction, and the dashed line there is showing the depth of these networks. The number of functions you're composing, and huge jump in moving from the 2014 winner to the residual network. And you know, Kai-Ming has this really visual way of showing that. So this is the 2012 winner, and then the 2014 ones, and then this is the rest. So you know, very, very significant increase in the depth of the composition that they're computing. So what's a residual network? So a typical network will consider two layers of it. The vanilla plain deep network, you compute a linear function of the input vector, then a nonlinearity, then another linear function, then another nonlinearity. So that's two layers of a plane network. In a residual network, you can think of it as doing the same thing, but with an additive identity function. So we're in the case where the input and output dimension is the same, right? So think of a computer vision problem where you're wanting to classify every pixel as, I don't know, the center of a face or something. So the input and output dimension is the same, and we're taking functions from x that are expressed as, you know, h of x is the original input x plus some nonlinear function f evaluated at x, and that nonlinear function is computed in a similar way, right? It's linear followed by nonlinearity followed by linear. Okay, so why is that a good idea? Why is having these identity components a good idea? Well, I guess first of all, so when we think of these things as compositions, nonlinear functions, now we should be thinking of the HIs as these double layers, right? So you know, for the cases that we talked about, you know, you should think of H1 as being x maps to x plus this nonlinear function. Okay, and you know, and I haven't said anything about, so we know that we're mapping from the input dimension to the same dimension. We have an identity connection, but these AIs and nonlinear function times a nonlinear function of BI times x, you know, this could be rather wide, right? So A might be a short fat matrix. Right, so think of that second piece as just, you know, a function from a rich non-parametric sort of family. Okay, so these are the family of functions that we're considering here. Why is it a good idea to introduce an identity connection? Well, the intuition is, and you know, as the authors argued and demonstrated with some impressive experimental results, that you know, so when you have zero-valued parameters, which is close to the state at which these simple first-order optimization methods begin, then the network's computing an identity function. So that's nice and well-conditioned, right? And that means you're getting useful feedback about the direction in which the output should be changing all the way throughout the network. You know, if you think about some very deep network of this sort that has these identity connections and near zero parameters, then, you know, everywhere in the network you're getting some useful information about when you're using a gradient method, you're getting some useful information about the direction in which to update some parameter. Okay, so that's the intuition. There are experimental results that support this. So these two graphs are showing what happens as training proceeds on two kinds of networks, a plane network on the left and a residual network on the right, for a particular image classification dataset, Sci-Fi 10. And the solid lines are showing the performance on test data, and the dashed lines on training data. And so the x-axis is the number of iterations of this algorithm, and the y-axis is error, smaller is good. And you can see for plane networks, as the different colored lines represent different depths of network, and as the depth increases, the performance on training data gets worse, and performance on test data gets correspondingly worse as the depth increases. So that's a failure of the optimization, because, you know, for a network of depth 56 can represent everything that a network of depth 20 can represent. I mean, you can ignore some layers, you know, certainly in terms of the representation, at least. And in the case of residual networks, the opposite happens. You see that as the depth increases, the performance on the training data improves, and similarly, performance on the independent validation data also improves.
Quick question. So maybe you mentioned it, but I guess at the end of the story, you have a number of outputs that's equal to the number of classes or something. So do they do this residual business
right.
up until that very final layer? Or?
So so I actually have a little bit to say about that. All of the results I have are for, D dimensions to D dimensions. So, everything has an identity connection all the way through. In practice, what they do is, so there'll be, reductions in dimension, and they'll have some linear map that takes you from D dimensions to some smaller dimension. It's not an identity map. I'll say a little bit about that later.
All these things exhibit a big discontinuity.
Yeah, I thought someone would ask that. So this is just part of the black art of training these things. At some point, they say, we have a certain step size and we don't seem to be making progress at this point. We'll change the step size to something much smaller and we make a lot more progress.
But that suggests that maybe that's when they throw in the test data.
Allegedly, they don't. All right, and in practice on some large-scale benchmark problems, this has led to really significant improvements over the previous state of the art. Okay, so there's been a bunch of related work, so the sorts of results that I'm going to talk about. Related work looking at the behavior of the optimization landscape and what implications that might have for first order methods like gradient descent. There are a couple of I guess a couple of the most closely related. There's this recent work of Ohad Shamir that says that a residual network with a linear function at its output doesn't do any harm in some sense, right? So if you have a linear function at the output and the f theta is parameterized in some sensible way, there are some conditions, then somehow that's not going to do any harm in the optimization in the sense that any stationary point gives you something that's at least as good as the best linear map. Right? So adding in this thing before the linear map is not harmful. So nice sanity check kind of result there. And there's the most closely related is a pair of results that we build on here for deep compositions of linear functions. So these are just linear functions, but parameterized in this sort of rather strange way. So this is due to Hart and Ma, and it gives really, I think, very nice intuition. So let's start with talking about their results. So the first is saying that if you have an invertible matrix, let's say its determinant is positive, then that invertible matrix can be written as a product of matrices that are close to the identity, and the more matrices you multiply up, the closer they can be to the identity. Okay, so this is a spectral norm here, and the big O notation is hiding some notion of scale of the original matrix. So that's nice, right? That's saying that if you, at least in this linear case, if you're wanting to represent things as identity plus something, then you can do that whether something is really as small as you like, as long as you're willing to go deep enough. Okay, that's the first result, and the second result is an implication for the optimization landscape. So let's think of the case that they had was a linear Gaussian model with this parameter matrix A. They wanted to parameterize A in this crazy way, right? A product of M matrices of the form I plus A, identity plus AI. And they're interested in minimizing the expected squared Euclidean norm. So if you were to use a gradient method here, this is an ugly non-convex problem, right? Because of the silly parameterization you've chosen for a linear linear quadratic kind of criterion. But it turns out if you keep these deviations from the identity small, then every stationary point of that quadratic loss is a global optimum. So there's this first order condition for optimality, right? If you find a point A1 through AM, so a point in this parameter space that has the gradient with respect to each of the AIs of the criterion equal to 0, then that corresponds to the A that you were seeking, trying to estimate. So there's a simple first order condition for optimality here. Okay, so that's very nice. So the second part of the talk is all about generalizing that to the nonlinear case. This is joint work with Steve Evans at Berkeley and Phil Long, who's at Google. The first result is when we consider a composition of m functions. The result is that if we want to compute a smooth invertible map, then we can spread that out through m functions so that every one of those HIs is close to the identity in the sense its Lipschitz semi-norm is small. Where close means order of log m over m for depth n. And just to be a little more, okay, so more intuition. So you can think of each of those HIs as being near identity maps that might be computed in this sort of a way, right? An identity plus something from a nice non-parametric family, and as this network gets deeper, this nonlinear piece can get flatter and flatter. Right? That's the message of the result. Okay, and to be a bit more precise, we're assuming that H is differentiable, invertible, smooth, which implies a bound on its derivative, because we're considering a bounded domain. So it's a Lipschitz function. It also has a Lipschitz inverse, and we're assuming this topological condition we have that the determinant is positive somewhere. Then, for all depths m, we can find a decomposition of the original function h into these h1 through hm, so that each one is close to the identity in the sense of this deviation from the identity is flat. It goes down like log m over m, and the composition is exactly the function h on this bounded domain. Okay, so I'm going to skip through.
Wait, what's the difference between the two previous slides? This one and the previous one that you wrote?
This one is precise, and the previous one is hand-wavy. Yeah. Right, so, I have specific conditions that we need to satisfy.
Can you say a little bit about the positive orientation condition?
Yeah, so wanting everything close to the identity means that we have to have our derivatives staying close to the identity everywhere in some sense, right? So the determinant of the derivative can't change sign if we're insisting on things being close. So, it's inevitable. Turns out it's only, a kind of binary condition.
And briefly, so the previous result was saying that if H is linear, then H1, H2, Hm can be chosen to be linear as well.
Yes.
So if H is nearly linear, can you quantify how nearly linear H1, H2, Hm are going to be?
Not any more strongly than saying the identity is linear and, this Lipschitz semi-norm of the difference is getting smaller and smaller.
You won't have any control on the derivatives, for example.
I mean, the proof might give some consequence of that sort because we actually can construct the HIs explicitly, and they inherit smoothness properties from the H. So if you have near linearity there, you'll get near linearity of these HIs, but we haven't shown that. I'm confident you could show something of that flavor, but I don't know how it would work out in terms of the parametric problem. Right, I'm going to skip past the.
What's the benefit of being deep here?
The benefit of being deep? Yeah, it's a good question. I mean, this result says that you can be close to the identity. You can be close to the identity everywhere as long as you're deep. And if you're shallow, you can't be. So the original H has nothing about, the closeness to the identity is like some finite thing.
Okay.
But being deep means you can get closer and closer at each layer. to the identity. And we'll see it plays into the next result. So I'm going to skip over the proof because I'm running way behind time, and say a little bit about the analog in the nonlinear case of the second result that Moritz Hart and Tenyu Ma had. And this is the notion of global optimality of stationary points. And here we're working in function space. So we're thinking about the same sort of criterion, quadratic loss. We define the minimizer of this H star, so the conditional expectation, and then consider a function that's a composition of things that are all close to the identity. Then you can show that all of the derivatives are bounded below by something that depends on how far you are at H from the optimum. So what are these derivatives? This is the Frechet derivative of the criterion Q with respect to each of the HIs. Right, so you're saying in what direction in function space should I move to decrease Q if I wanted to update HI. The norm of that is only small when QH minus QH star is small. Okay, so unless you're close to the optimum, you can't have a small derivative there. And under the assumption that this norm of H minus H star is induced norm is defined. And things are differentiable. So differentiability condition on H. So very much the analog of that first order result. It says that if you have zero functional derivatives, then you've reached the optimal value of this criterion.
So does this mean we have, say my H's were all in some Hilbert space, does this give me some kind of implementable procedure? I do some sort of gradient method in Hilbert space? And
right. If you're thinking of this condition that the H's are close to the identity is a convex condition, you could work with trying to optimize things in this convex space. So the natural thing, this is just a first order condition. So it does suggest that a gradient method might be an appropriate thing, but you have to keep in mind this constraint, right? You have to stay close to the identity.
So the conditioning somehow gets worse as it gets deeper because epsilon is log m by m.
Right. So the log m is kind of problematic when you see
you're going to get kind of like 1 on m-ish conditioning.
Right.
But maybe that's the
which I'm hoping is loose. Yes.
Maybe it does not. Yeah.
You would hope that.
The way it's written here, it seems to be uniform in I. Is that a typo? Or?
Uniform in I, but epsilon is log m over m.
No, because
it's uniform in I. What?
Okay.
We're good.
Yeah.
Okay. So, so it's telling you that if you have a suboptimal composition and you're close to identity everywhere, then there's somewhere in function space to move. It's just a first order condition for optimality. So in the sense of when you're thinking in terms of these functional gradients, you don't have local minima and you don't have saddle points. So but of course in any particular architecture that you might consider parameterized architecture, you should expect local minima, you should expect saddle points. And what that's telling you is that the direction in which you want to move might be orthogonal to all of the directions you have in some function space. Over that. All right, so I am running out of time. So I wanted to get to at least stating, I'm going to skip over all of this, I wanted to get to at least stating the results from the second part, which is thinking about implications for optimization. Natural consequence would be I'd like to do gradient descent here, right? I have to keep in mind that I should keep inside this region that's close to the identity, but can I use first order methods that exploit these sorts of properties? So we went to this is joint work with Dave Humboldt at UCSD and Phil Long at Google. We considered the case of deep linear networks again. So going to this really crazy parameterization of a linear function, and considered just simple first order methods. And I think I'm going to skip to the very end and just give you the high level view. I have like 2 minutes, right?
7.
7 minutes. Okay. So I'm going to tell you a little more then. So, okay, so what we're considering these, deep linear residual networks, which is a fancy way of saying, product of matrices. Those matrices we think of as being close to the identity. And we're interested in minimizing a loss function that's the squared Euclidean, expected squared Euclidean norm between the f theta of x and y. And we're going to use a gradient method to do that, and we're just going to assume that we can compute the gradient exactly, right? So the gradient of this loss function. We'll make our notation a lot simpler by assuming that we have this symmetry assumption that the covariance matrix of the x's at the second moment is the identity, and we'll assume that the y's are given by some linear function of the x's, which is without loss of generality because of the projection theorem. And I guess I don't need this slide for this audience, but I'm giving this talk. I've had a lot of pushback from this assumption, but it is without loss of generality, right? If we're looking at the expected squared difference, we can just replace y with the least squares map and replace our criterion by this, and there's some other quantity that has no impact on the criterion or on the gradients with respect to theta of the criterion. So that's our problem. We have our linear function that we'll use this notation theta 1 through L of x, meaning the product of these matrices. And our gradient approach starts off at the identity matrix and then does a gradient update. So this is what the gradient with respect to the matrix theta I looks like. It's this second term without the step size eta. That's the optimization method that we consider. First result says if you start off at the identity matrix and the loss is sufficiently small, right, so you're sufficiently close to the least square solution, then you'll approach it exponentially quickly. And I'll skip over the argument for why that happens. Which is not so interesting, right? It's just saying if you're in this sort of basin of attraction, then nice stuff happens. You should expect that. I think more interesting is if you consider the case of symmetric maps, then we have something like at least necessary and sufficient condition. So if the least squares map is positive in the sense of, so a matrix is positive if it has a positive inner product. When you put any vector into it, you get a positive inner product out, and we quantify that with this gamma, right? So we've got under the assumption that our least squares matrix is symmetric, which makes things really very simple. If the matrix is gamma positive, then we get this exponential convergence. So start off at the identity, and we get exponential convergence. For the symmetric case, if the matrix is not positive, so if it has a negative eigenvalue and the depth is an even number, turns out this makes things really trivial, then it's hopeless, right? We can never solve the problem. So positivity seems to be an essential thing in the case of symmetric matrices. And again, I'll skip over the proof there, but it's really, the whole idea is in the symmetric case, everything becomes diagonal, right? So you have these crazy nonlinear evolution, but it's completely decoupled. They're scalar nonlinear equations. So that's really nice. Okay, I won't say any more about that. So when you move away, the assumption that the least squares map is symmetric is kind of crazy. And when you move away from that, we can still get this sufficient condition that positivity is enough. So if you have a gamma positive least squares map, then there's some algorithm that converges to the optimal thing, but it's being a little careful about staying close to the identity, staying positive rather, and spreading the computation out evenly across the layers, which keeps you close to the identity. So this approach, this optimization method, we've called the power projection. You take a gradient step, then you project the linear map computed by everything onto the set of gamma positive linear maps, so keep things positive, and then you balance out the think of it as balancing out the deviation from the identity through the L matrices. So this balanced factorization is just the notion of making sure that all the singular values are spread out evenly through those matrices. And there's an easy way to do that using a polar decomposition. So that was super fast, but I guess the summary slide. So if we start off with the identity and that's good enough, then we get this nice exponential convergence. If we have a symmetric map, then positivity is enough for exponential convergence, and a negative eigenvalue means we're in trouble. And if we have a positive map without the symmetry condition, then this sort of regularized approach, this approach that keeps us positive and keeps us close to the identity by spreading the computation out, spreading the scale out among the matrices, again converges exponentially fast. Okay, and of course, big question is what can you do in the nonlinear case with those sort of methods? Stop there.
So on the first part, so you have results on the estimation error. Do you know of any results for deepness for the approximation error?
No. So I had, there's this, I mean, not beyond that, the slide where I showed two references for, I guess, both for ReLU nets, right? So there are these examples of functions that you can compute in a depth. So I guess there's one more that I didn't quote there. So there's a result that says there's a function you can compute in depth k squared. If you want to compute it in depth k, then you need exponentially more ReLUs in order to do that, to approximate it to any non-trivial sort of degree. So that's going from k squared to k. There's another result that says if you go from 2 to 3, then you can have a similar exponential, 3 to 2, you can have a similar exponential growth in the number of parameters that you need in order to represent things. That technique seems to be tied to 2 and 3 layers. And these are sort of examples, right? Here's a bad function that we can compute easily and can't compute easily with a shallow network. It's falls far short of a kind of rate of approximation result you might like.
So I guess at some point I get lost about the role of the identity in this whole thing. I mean, is it here because it makes your life easier? Is it here because it's like vaguely justified by ResNet, but is it really what's happening? Is it should I view this as where I should center my parameter space? I get a little, I mean, I can see why we can actually say things for functions that are close to the identity. I just don't know if it actually has a central role for
so the intuition is that being close to the identity makes things well conditioned, right? It means that you're somehow seeing far through the network. And so if you have this situation where everybody in front of you is close to the identity, then you know the impact that you will have on the output, and you're not going to be in some nasty ill-conditioned setting where things are really unstable in terms of what you do because of what the guys in front of you are, the impact of the guys in front of you when they change their parameters as well. I mean, I think that's the intuition that's borne out by the sort of quantitative results that say keep close to the identity. And
let me push this intuition and say my function is the identity, in which case I have a pretty nice landscape. Yep. What is trading me off from doing this? Like, did you present any results that said
it's not a very useful class of functions?
Well, but useful is not a measurable. It's not a measurable trade-off.
Can't argue with that. I don't know. I guess I don't understand the question.
Well, I mean, I guess it goes back maybe to Francis. Like, are there useful functions that are close to the identity?
Oh, right.
They're certainly more useful than the identity.
Yeah. So the representation results in the second part of the talk is they're saying that you give me a function that satisfies that list of properties, and I can represent it as a composition of these near linear functions, near identity functions, a composition of those. And so that's not saying you start off with a near identity function and you want that to be useful for some statistical modeling sort of problem. It's saying, start off with some function that satisfies these conditions, and I can break it down into near identity functions, and that's useful for optimization. Right? So that was the message of the second part of the talk. I mean, you can criticize the conditions that we had to impose on that that function that makes things work, but being close to the identity is not one of those.
Okay, but Hart and Ma was that, right? Hart and Ma started by
Hunt
saying...
and Ma was that in the case of products of matrices,
Yeah.
yes. That's right.
Pradeep?
So I guess related to the first part of the talk where you showed that the statistical complexity is essentially depends on the product of the spectral norms.
Yeah.
So I guess there, if each of these guys are close to the identity, then it won't blow up as opposed to...
That's right.
If it's the
That's right.
If it's
And
bounded-
actually, there's a refinement of that result. There's sort of fudge factors that appear in that second term. In the ResNet's case, they depend only on the deviations from the identity. So that, things are slightly better in terms of that, additional factor in the case of things close to the identity.
So in successful networks, so does it match what's... So in the sense that, is it actually close to the identity? Or does the product actually blow up?
Right. So those products don't blow up in a crazy way as when you look at deep networks that are used for. Okay. So there's some caveats. So there's this nice empirical paper that a bunch of people did at Google, looking at fitting Cipher 10 data, so image data, with classifying things into 10 classes, and they split that in. They looked at the regular case, just the actual labels, and they looked at random labels. So there's nothing predictable there. No information in the images for the random label case. And the main observation there was that actually these stochastic gradient methods could fit the data in both cases, and perfectly well. But of course, in one case, you can actually predict something. On validation data, you get I don't know, 20% error or something. It's doing something non-trivial. And of course, in the permuted labels case, it's doing something totally trivial. So there's a huge difference in the misclassification probabilities, even though they're both doing perfectly well on the training sample. And in that case, actually, you can go and measure the product of the spectral norms throughout the network. And in the first case, you find something that's really rather small. In the second case, it's like an order or two of magnitude bigger. Right? So you're getting a network that is way more complex in the second case. And this is, when you go and, you can plug the numbers into the bound and you get two different numbers that are way bigger than one. But, in terms of how they compare to each other, I don't have it here, but there's a slide where you can show that given some scaling of how these things evolve in the two cases, you get a pretty good match between the evolution of the bound and what happens to these misclassification probabilities in these cases.
Time for a couple more questions. Okay, we have like 6.
So when you have these deep nets, it seems like they should have some sort of stability property. It can't matter what you do in the first layers. You could even do something random.
I guess. I don't know. What are you getting at? What's the?
So does it really matter what happens in the top layers? Is my
in the first layer where you're processing the input. You could certainly come up with examples where you're throwing
so
information.
much over-parameterized. Anything you do in the top layers
Could be
washed out.
right. So if you're computing some sort of invertible function in the first layer, then it shouldn't matter. I guess that's true. And the sorts of conditions that we're looking at here, where you're keeping things close to an identity, guarantees that you can invert these functions. So yes, I guess that's a consequence of that sort of result. That's right.
One last one.
Maybe I missed it, but does any of your bounds say that you can't go too deep?
So no, it's worse than that. There's nothing that really demonstrates in these pieces. There's nothing that demonstrates that pull the pieces together and deep is better. right? I mean, thinking just of a linear case, right? This is a crazy way to parameterize a least squares problem.
Sure, but apart from cleaning cost, there seems nothing that prevents you from
Going deeper, right? I mean, I guess.
Estimation error.
Yeah, the estimation error has this product through the layers. I mean, it was pointed out there's a log m over m there. The log is sort of problematic here, but you might expect that could be improved to the same as the linear case. But even then, it's not demonstrating that there's an advantage of doing that. But yes, I guess the other thing that has a depth dependence is in the estimation error part of the talk, that the fudge factors there, that necessarily grows with the depth of the network. I guess there are improved results, the Golowich, Brooklyn, Shamir result for homogeneous nonlinearities that avoid that dependence. But yeah, so it's unclear, I guess.
I think we'll have to continue this over lunch, and let's thank Peter again for